William. William?
I think Will has
Okay. Right, so last week we were talking about the Anthropocene. We were talking about all sorts of nasty, horrible stuff that's happening to the planet because of the obsession with fossil fuels and production of carbon dioxide. Yeah. 20 minutes to do this. So I want to try to explain to you, and you can write this, the greenhouse effect. Okay. And the greenhouse effect is a natural phenomenon. This is a natural phenomenon. Like, humans aren't totally responsible for it. By which the temperature of the Earth rises because heat is trapped by its atmosphere. So if planets have atmospheres like Venus does, possibly Mars did at some point, it's got a very, very thin atmosphere at the moment. The Earth's definitely got an atmosphere. The sun's radiation falls on it. Some radiation gets in, and it doesn't get out again. The atmosphere acts like a one-way door, a one-way window. You can see in, but you can't see out. And then the temperature goes up. And Venus's atmosphere, it kind of doesn't matter because it's a temperature of hundreds of degrees Celsius on Venus. So it's not the right temperature for sustaining life. What sort of temperatures are needed for life, do we believe? Above zero. Yeah. And so we got the kind of lower limit. Yep.
Like between 1 and like 100 Celsius. So the water doesn't freeze or boil.
Absolutely. Yeah. The temperature, basically the temperatures we've got on Earth.
So that means the average is
yeah. I mean, obviously, you know, we're here and we have life below zero. But we adapt to that. Yeah, average. Basically, the average temperature that we've got is suitable for life as we know it.
I want the average temperature of here in Finland.
Depends where you're looking. Average temperature for Oulu, I believe, is something like 6 degrees Celsius. I believe, but that will obviously be different. Every time I look at the weather map, Utsioki is at minus 15 degrees Celsius, even in summer it seems. So. Okay, so actually with Venus, if we take the view that you can't have life above, I don't know, an average temperature of 60, 70 degrees Celsius, then you know, this is in the zone where it's just too hot anyway, but Earth is in a very, very sensitive zone. It's called the Goldilocks zone, where it's just right. Like Goldilocks and the Three Bears. She couldn't eat Daddy Bear's porridge because it was too hot, and Mummy Bear's porridge was too cold, but Baby Bear's porridge was just right. Yeah? So we're in the zone that's just right for life. Our planet has got an atmospheric composition that's just right for life until we come along and ruin it in some way. Okay, so this is kind of more physics, but this is how it goes. So, going to draw a diagram, and it's very simple. First of all, we have the sun, and when we draw a sun, we put a smiley face on it, and we draw rays because we're about 4 years old. Why not? Let's revisit childhood. And then we have the radiation falling on the Earth, only that's the ground, so it's green. And we have some trees. And then we have the sea, or water. And also in the sea, we have floating around prizes not available, but can anybody guess what I'm trying to draw? A donkey floating around in the sea. It's not meant to be a donkey, but it does look donkey-like. Can't do it.
I see narwhal.
A narwhal. That's a narwhal.
Polar bear.
A polar bear. Okay, my art isn't too bad. Okay, ice.
Then it's too close.
Sorry?
It looks too close.
What looks too close?
Because polar bears can't live technically that close to like grass.
That's true. I know. But the sun isn't that close to the Earth, is it?
Depends on the angle.
Oh, you pedant. Yeah, it does. It does. Okay, so we've got land, sea, we've got ice. Okay, there's a reason I've chosen those three things. You do not have to draw the polar bear.
Too late.
Too late.
Now,
I just love computers.
me too.
No, go away. Now I don't like computers. Right, where is the...
You need to do it at the you need to click the picture and then right. So the drawing was good.
The drawing was good.
It was good enough. No,
Kiitos. Okay, so I'm going to draw the imaginary blanket around the Earth here. That is the atmosphere.
What's that?
Go extinct, you stupid drawing.
Okay.
Okay, so the sun's radiation comes in, and the radiation that we get is visible light, it's heat, etc. So it falls on the different surfaces. What will the radiation do when it falls on ice?
Melt it.
Melt it? It might. The polar bear gets hot, Some of it will be absorbed, but on a clean ice sheet, 99.9% of it is going to be reflected. Yeah, and that radiation will be reflected straight out. Yeah, and that is really, really important because that radiation, light, ultraviolet, even heat radiation, you guys know you can get a suntan so easily by walking across snow because the radiation is reflected from the snow surface, ultraviolet light. It's also pretty hot. It's reflected from the surface. It's blinding to look at. You need sunglasses in the winter. And that radiation bounces straight off. It means then that very little of it is absorbed. Now the sea will reflect a certain amount, but some of it is absorbed. The land, usually being darker and having a more rough surface than the sea, will absorb the radiation, and the forest areas will do what they do best to synthesize. So some is absorbed there as well. So effectively, if it's reflected, it has no impact on the Earth. But if it's absorbed by the Earth, the land and some of the sea, or the whole sea, will also heat up, but it will then re-emit radiation. But it will be of a different frequency. Okay? Absorbed and re-emitted at a different frequency or wavelength. Now that's some quite complicated physics. And luckily you don't have to understand it all. And I'm going to give you a bit of a cheats explanation, but it will work. Okay, you don't have to draw this. It's a horse. Almost.
Donkey.
An ass. A zebra.
It's not an ass. It's a zebra. Yay! How did you know? Horse. There are stripes on it. Yeah. These are the black areas. These are the stripes. Yeah. So this is a thermal image. Heat, light, everything, the same everything, falls on the whole zebra. The zebra absorbs the heat, but it re-emits it at a different wavelength. So it shows up as different colours. And that's what the Earth is actually doing. The energy from the sun is absorbed, and some of it is then re-emitted. The problem is, the stuff that's re-emitted doesn't get out of the atmosphere, or not all of it. Okay? So it is re-emitted at a different frequency or wavelength, which cannot pass back out of the atmosphere because of greenhouse gases, e.g. carbon dioxide. So when that radiation falls on carbon dioxide, because of the wavelength of it in some complex physics ways, it doesn't get out again. So that heat is trapped inside the atmosphere. So that extra heat energy, because we put extra carbon dioxide into the atmosphere, stays on the Earth and it melts more ice. And when more ice is melted, it means that less energy is reflected out, more is absorbed, and it's re-emitted at a different wavelength. So more heat trap it stays in. So the ice sheets are really, really important. Once they start melting, they ain't going to stop melting until the amount of carbon dioxide is changed. Okay, this does happen naturally, and the Earth for many, many years has been in a lovely atmospheric balance, where the gases that are in the atmosphere allow a certain amount in, a certain amount out. Passage around the sun allows a certain variation in temperatures. But because of what we're doing with the Earth's atmosphere, just by changing the carbon dioxide, the balance is now wobbling a little bit too much. Okay, it was moving along quite happily. It's now beginning to shake a little bit too much, and it's like an ice skater that kind of knows it's going to fall over. They're going to fall over unless something very dramatic happens and they learn how to skate properly. So this is a very quick revision. I'm going to show you a useful graphic. Shame we haven't got enough time to actually write it down. Okay, this is the atmospheric composition of the of dry air. Dry air. 78% nitrogen, 21% oxygen. You can write this, yeah. Argon, 0.9%. Okay. The pie chart that we've got really shows it quite dramatically. Loads and loads of nitrogen, loads of oxygen, tiny amount of argon, and then 0.04% carbon dioxide. 4 parts per million. That seems absolutely crazy. It's not the majority gases in the air that are causing the greenhouse effect. It's this little devil, carbon dioxide, that is present in 4 parts per million. So if you imagine everybody in Finland right now, all what, 6 million? 5.8, yeah? 5.8. So you then pick how many of those people, if each person in Finland represents the air, how many of those people would be carbon dioxide molecules? 78% of 5.8 million are going to be nitrogen.
About 40. 24.
24?
If there would be 6 million.
If there's, yes. If there were 6 million people, 24 of them would be carbon dioxide molecules.
Whoa.
Not many. Has a huge impact.
How does it affect so much?
Because it's very, very small and very, very powerful. bit like a really toxic fart. Not much gas, but we all know it's been done. Okay, and the problem is that 200, 300 years ago, there were 2 parts per million. Human beings have been responsible for those extra 2 parts per million being added. It's really pretty darn scary. There are other greenhouse gases. Methane is another one of them. Ozone actually also is one, but there's not much of that in the atmosphere. But we've got to be very, very careful with the gases that we are adding. Okay, that was the really, really condensed, short version. But I hope you've got the message. And we'll do a bit more on Friday.